Okay, mic is on. So we are going to look at some of these non-ideal VI effects. I'm not going to go through it again. We already went through it in the slides. The previous lecture we had mentioned something, but the recording was not proper because of the volume. So I'm just going to list it. It's very easy, and we already discussed it in the class uh, meeting. So we will not go through it in detail again. I will just list it. Okay. We have channel length modulation. Okay. And then we had velocity saturation. And then there was mobility degradation. And then last one we discussed was drain induced barrier lowering. So we discussed all of these. Just give a quick test for you, okay, to see if you have understood it properly, since we have already discussed it in the class. Generally, every semester once I teach this, but thanks to Corona, I'm doing this for the third time within 1 week period. So I don't know how useful it's going to be, but whatever it is, these are important effects, especially sometimes we teach things that are not useful because they were historic, etc. But this is completely opposite. This is only valid today as we look at more and more short channel devices compared to the earlier generation of VLSI, where all devices were in the micrometer range. Okay, so channel length modulation. So let's make a small table. Current, okay, and then short bar, long channel, okay, and okay, that's enough. So channel length modulation, the current increases, okay, that is what we discussed. The current increases in the saturation region. It has no effect in the linear region of operation. So one question I want to ask you, does it affect both NMOS and CMOS transistors, or only NMOS transistors? Because through the class, in the slides, and in the this thing also, we have been only looking at the VI characteristics of NMOS. Does it affect CMOS transistor also? So this is something for you to think, okay? And short bar long channel, this doesn't affect long channel devices. This is only for short channel, okay? Short channel means in the range of, say, less than 200 nanometers. So 200 nanometer is not a technology node at all, but 180 nanometer is a technology node. 135 I think is a technology, or 130, sorry, 130 nanometer is a technology node. 65 nanometer is a technology node. So these are all technology nodes. They don't move continuously. 180 don't go to 179, 178, 177 like that. They jump, okay? So this is for only short channel devices. It doesn't affect long channel devices. Next one, velocity saturation. So we already discussed. I'm not going to discuss the actual effect, okay? Because of velocity saturation, current is lesser than what is actually predicted. That is the first thing. And the second thing is, does it affect long channel or short channel? It affects mostly short channel devices, because in long channel devices we don't see that much of the effect because the distance they have to travel is more. So more important in short channel devices. Mobility degradation, again the and long channel, okay. And last, drain induced barrier lowering, the leakage current Okay, this has the last one. The gate is not turning on the transistor. The transistor is supposed to be off. Okay, this is not an effect where we want the current to flow at all. But because of this drain induced barrier lowering, even when the gate is off, the transistor is supposed to be off, the drain voltage is able to generate some current because of the effect it has in the channel region. The drain is having some positive voltage and it acts like the gate terminal itself. And that particular effect is called as drain induced barrier lowering. Definitely, this is only in short channel devices. It has nothing to do with long channel devices. Okay, so the effects we're not going to discuss again. It's discussed multiple times, and it's very simple to understand also. One effect that I didn't discuss in the slides is another very important phenomenon, which is called as sub-threshold conduction, and the name itself tells most of the things. We have a particular voltage level called as threshold voltage, and that threshold voltage is some number 0. 0.4, 0.5 for NMOS, minus 0.4, minus 0.5 for PMOS transistor. Now in sub-threshold conduction, which means that from the name itself, okay, the gate voltage is below the threshold level. That is, if the threshold level is 0.5, gate voltage is 0.2 or 0.3. Okay, for our simplicity's sake, we have considered that IDS equal to 0 in any numerical. For example, okay, if VGS is lesser than VT, directly we write IDS equal to 0. But actually it is not equal to 0. We are not going to ask you to calculate that, but it is important to know that current will be flowing, okay, and that current is called as sub-threshold current. What is the meaning of current will be flowing? You might ask, how can current flow, right? It is quite similar to our normal current flow. The charges are being attracted by 0.2 volts. Okay, what is the difference between 0.4 and 0.2? The number of charges is going to be lesser. So for example, if I apply 0.5 volts at the gate, okay, that might attract 10 power 15 per centimeter cube of charges. If I apply 0.1 volt, it is still going to attract, maybe not 10 power 15, but it might attract 10 power 10. So the current magnitude is reduced by 1 lakh times. Okay, but it is still not 0. The problem with these currents is they're always flowing. Okay, that is, even when I am 0.1 or 0.2, the current is going to flow, and that is why we have a separate term for that. It is an important term called as sub-threshold current, and this is very important also because in the real situation, okay, this is our input. We generally, if we are talking about digital circuits, for example, in Verilog, all the waveforms will have zero rise time and fall time. They will be like a square wave, right? But in reality, there can be no waveform that is having zero rise time. Any waveform that is generated as part of any circuit, okay, digital, analog, RF, doesn't matter. It might be fast, but it cannot have zero rise time and fall time. So it is going to take some amount of time to go from here to here. And this range, okay, where it is going from 0 to Vt, that is where the sub-threshold conduction is happening. That is, if I am having some transistor that is going from 0 to high, okay, at 0 to Vt also it is conducting. Above Vt, I know it is definitely conducting, there's no doubt about that. But between Vt and 0 also there will be some conduction which is called as sub-threshold conduction. So I'll just summarize that here. Conduction Okay, this is the condition. That is, VGS has not crossed VT. It is still lesser, but it is greater than 0. So here also some conduction will flow. Conduction of current when okay, so this is not something that is participating in the main functionality. This is part of the somewhat similar to our parasitic. So this is also in some ways a parasitic effect of the way in which the transistors are designed. So it is contributing only to the leakage part of the current. So this is also a non-ideal effect. Okay, and one more very important thing nowadays, especially as devices that are dependent on a battery are becoming more and more important. Okay, the best example for this situation is home automation. In home automation, generally there are a lot of physical devices that are connected to, say, some single, maybe even your Alexa or Google Nest type of device, right? And the thing with all of these devices, and maybe a human being is also involved in that, all of these devices are relatively slow, meaning they don't operate in gigahertz frequency because many of them are mechanical devices. For example, a refrigerator, right? Now, refrigerator, this is, I think this is still science fiction, but refrigerator, there might be some, this thing that tells you how much milk is there in the refrigerator. So it's going to be a one-time signal, right? Every nanosecond, you don't want to know how much milk is there in the refrigerator. Nobody cares. Maybe even once in a day you do this, it's more than enough. Similarly, you might want to open a door. So there will be a signal that is sent to a mechanical relay, because whenever you're thinking of things like door, etc., there should be a relay, right? And relay is a mechanical device and it operates at a much lower speed compared to our electronic devices. So in those type of situations, okay, the whole circuit, that is our central automation circuit is there, right? The electronics behind the Alexa or the Google Nest, that whole system, okay, is designed in sub-threshold voltage only. That is, the power supply itself is zero point 0.2 volts. There is no VDD equal to 2 volt, 3.3 volt, nothing. VDD equal to zero point 0.2 volts, and all the operation happens between 0 and VDD. So how does it work? Because current is still flowing, right? The only effect of sub-threshold operation is the speed is much lower. What is the, ideally we need current and we always say that we want more current to increase the performance, right? Opposite of that is, if you have less current, performance is lesser. But just like we described this home automation type device, we don't need high performance. There, more important is battery life. So if you are working, if your design, okay, the whole design is in sub-threshold operation, the performance is lower, great, okay, that's a problem. But the bigger advantage is your battery life increases exponentially because the power consumption is much, much, much lower. So your home automation device, if you just put it on top of your ceiling, every day I can't go and recharge the device, right? But if you design something like this, maybe only once a year you need to replace the battery. So there are complete designs nowadays, especially not a microprocessor. There is no microprocessor that is designed in sub-threshold region, but there are systems, there are designs that are completely operating only in sub-threshold region. They are designed to operate in sub-threshold region. So this is, of course, a non-ideal effect, but people have taken advantage of this and they have designed circuits also. Okay, so this is one non-ideal effect that was not covered in the slide. I just want to mention this briefly. And again, we are not going to ask you to calculate the current in sub-threshold region. Okay, for even though it is there in the book, we are not interested in that. Just be aware that there is a effect called as sub-threshold conduction. Okay, so the next part of our syllabus, okay, let me just check. Okay, so finally we come to the point where we are finally ready to design circuits. We know everything about the transistor, we know about the current, we know about the capacitances associated with the transistor. So first we will design some circuits, right? The basic gates, and then the compound gates, and then some special gates like mux, etc. Then we will design also the sequential components, in particular the latches and registers or flip-flops, and all that will be part of this unit. And another thing that we will see also is how to draw the layout. So layout is a very important component. Even though we have tools to draw layouts, we need to know how a layout is actually looking like, and for simple circuits, how to draw the layout. So that is what we will do in this unit, rest of this unit. Later units, we will talk more about the speed of operation. We will see how to improve the performance of the circuit, and there we will be talking about the delay. So right now, just because we are beginning with simple circuits, we are only going to look at functionality. Functionality means given a truth table or given a logic expression, okay, how do you design a circuit? And I also mentioned this in the slide, very important. Do not get confused between terminologies, meaning if I say circuit, okay, it means that it has to be at the transistor level. It cannot be at the gate level. Don't draw the old expressions you have, old diagrams you have for AND gate, NAND gate, etc. That is not what is meant by circuit, okay. That is a logic level schematic. This is a circuit level schematic, okay. And in digital circuits in particular, there are only two components. The circuit can be 10,000 gates, 1 lakh gates. There is only a NMOS transistor, PMOS transistor. There's no other components. The only other thing, of course, is metal interconnections. So the whole circuit is just transistors. Okay. So before we go in, we will just remind ourselves of NMOS and PMOS, this thing, functionality. Okay, and NMOS. Okay, so generally the control is through the gate terminal. So whenever almost any digital circuit, any style of circuit design, when we say the input is given to the transistor, the input is to the gate terminal. Okay, we don't give input to source or drain terminal, because the controlling of the transistor is happening through the gate terminal. Okay, so any signal that is generated and we want to control some circuit with that signal, we have to give that signal to the gate terminal. The type of the circuit, that will determine how many transistors are there, are they connected in series, parallel, all that is a separate issue. But any input, okay, to a digital gate means it is given to the gate terminal of the transistor. It is not given to source or drain terminal. Okay, and we will just look at the equivalent circuit. PMOS transistor, this is the circuit symbol. Okay, and when gate equal to 1, this is represented by a open circuit, and when gate equal to 0, the same PMOS transistor acts as a closed circuit. So for the basic functionality level, this is all we want. Okay, the 3-terminal device becomes a 2-terminal device because gate is out of the picture. After the gate has effect, it will just be on or off. Hi pigeon, don't come in. Okay, so gate equal to 0, it is a, sorry, gate equal to 1, it is an open circuit based on our analysis of the transistor structure, etc. Gate equal to 0, it is a closed circuit, and exactly opposite for the NMOS transistor. Okay, gate equal to 1, NMOS transistor is on, gate equal to 0, NMOS transistor is off. So this again I mentioned in the slides also. I have mentioned in the other video also, without the volume. With the volume also, again I will mention, do not get confused in this particular information. Okay, which transistor is on when we have only two types of transistors, so it should be very clear. If you make a mistake in this one, then everything else will also go wrong. You will be able to you will not be able to go right in the other steps. So this is very important. Do not forget this. Okay. So based on this thing, we can have connections in series, parallel, etc., and we can come up with different types of functions. So we will look at the basic gates to begin with. Okay, so I will draw the gate, and after the analysis we will see what is the function. So first I will draw a gate that may be anything. Okay, so this is an example of a two input gate. There are two inputs, A and B, and we're not going to do the inverter. Inverter we've done in the slides. It's too simple. We will start with a two input gate. Okay, and we will draw the equivalent circuit for different input combinations. So we have two inputs, so we will have four input combinations. Okay, so we will start with AB equal to 0 0. Okay, so start with AB equal to 0 0. Remember the previous diagrams we had drawn, which transistors are on, which transistors are off. So give both AB 0 0. A is connected to one PMOS. The same signal is connected also to one NMOS transistor. So we can draw the equivalent circuit for all four transistors. Okay, and then see what is happening to the output. So 0 0, which means that both PMOS transistors are conducting. Okay, very simple. Based on our knowledge about the gate control, just replace every transistor with either open circuit or closed circuit. It cannot be anything else. This is simple digital operation. It can be open circuit or it can be closed circuit. That's all. So this is the equivalent circuit for AB equal to 0 0. So clearly we can see through this path or through this path, actually through both paths, not or, because both are closed. Through both the sides, output is connected to VDD. So what is the value of the output? It is equal to VDD or logic 1. Okay, and another thing, it is not connected below. That will be a big problem if output is connected to both above and below. Okay, we will be at a bit of a problem, and there is a whole logic design family called as pseudo NMOS. When we come to that, we will see what happens, but for now at least, that case we have to take care through our design. We'll talk more about that in a little bit. Okay, next case. Okay, so A equal to 0 and B equal to 1. So wherever you have A and B, A equal to 0. So which means that left hand side PMOS transistor is conducting, Right hand side PMOS transistor is not conducting. Then A equal to 0, which means this is not conducting. Second transistor is conducting. Okay, so this is the equivalent circuit. Now we have only one branch. There are two parallel branches. Only one of those parallel branches is conducting. Will the output be at the same value as this one? Here there were two parallel branches conducting, but here only one parallel branch is conducting. Will the output be the same? What is the answer? What do you think? It will be the same. Okay, the only difference between this and this, as you will understand later, this goes from 0 to 1 faster, but the level reached, okay, is the same here and here. There is no other difference. So for example, here the amount of time taken to reach 1, okay, this is 0 1, this is 0 0. It goes fast. Other than that, the level reached is exactly the same. Even if there is one branch through which the output is connected to VDD, or maybe later as we will see to ground, okay, the level of the output reaches the perfect value of VDD. There is no voltage division or anything like that. Okay, and also below, since the first transistor itself is open circuit, it cannot be connected to ground. It is only connected to VDD. This is the same as this, only thing it is somewhat like a mirror image. And output also equal to 1. Okay, and the last case, output equal to, definitely it is 0, because there is no way the output can touch VDD. It is completely disconnected through both the parallel branches, and both the NMOS transistors are conducting. Output equal to 0. Of course, this is logic 0 or ground. Okay, so this is the way to analyze any circuit. Based on the input combinations, draw the equivalent circuit, and once you draw the equivalent circuit, okay, you can evaluate all the possible options. So once you have evaluated all the possible options, then you can go from equivalent circuit to truth table. And truth table, it might be some gate that is part of our basic gates, meaning it has some name, or it might be some compound gate, which means that you have to evaluate the function with a K map or something like that. But many times by looking at the gate itself, you will be able to evaluate the function. After you get a little more practice, by just seeing the gate, you will be able to tell. Even these are of course very simple. This is one of our basic gates. This is from the truth table. This is nothing but a 2 input NAND gate. Okay, and this is one of our basic gates. So definitely there is no need to remember this. I mean, this will keep coming again and again. But the compound gates, okay, those also you will be able to tell the function by just looking at the structure. That is one thing. Another thing is, we mentioned that the output, okay, is connected only to VDD or to ground. That is in all the three cases. First three cases, output is connected to VDD. The last case, output is connected to ground, but also there is no connection to VDD. So definitely the output is connected to only one, that is either VDD or to ground. Another thing to analyze is, for some input combination, if the output is not connected to VDD or to ground, that is also a problem, because we cannot have, for example, that is what is called as a high impedance. There is a separate class of circuits called as tri-state gates. There will be a third state, okay, where we are by design requiring a high impedance state, but for our normal gates we are not allowed to do that. So in the future also we will mention this, but this is also another important thing, that is the output node should be connected to exactly only one level, either VDD level or to ground level. It should not be connected to two, that's a problem. It should not be connected to zero also, that's also a problem. So exactly always one particular level the output should be connected to. Okay, so we will draw some more gates. We will not do such a detailed analysis. So we'll finish off the two input gates before going to the three input gates. Okay, so output equal to A plus B the whole bar. So this is our two input NOR gate, and you can do the analysis by yourself just to see if the truth table is equivalent to that function. Okay, and we will also draw three input gates. Okay, so three input, two input to three input is very simple. Just add two more transistors, one PMOS and one NMOS, and in the same manner in which the previous were connected. So in the previous case, there were two transistors in parallel in the PMOS, add one more PMOS in parallel. There were two transistors in series in the NMOS, add one more transistor in series itself. So very easily we can go from two input to three input. So this is A into B into C the whole bar. Okay, and another thing you might be thinking, does the order matter? A B C we have written like this, A B C we have written like this. Can I write A B C here, and in the bottom I put C, A, B. If I do this, okay, is it still A, B, C the whole bar? Or even the top I change, instead of A, B, C, I put B, A, C. And the order is different. I put B, A, C here and I put C, A, B here. Is it still A, B, C the whole bar? Yes or no? The best way to answer is equivalent circuit. Okay, and the answer is it does not matter. You can have the above in any order, the below in any order. The only requirement is these three transistors have to be in parallel, these three transistors have to be in series. As long as you are maintaining that structure, the order of the inputs above or below doesn't matter. They don't have to match with each other also. If you are having doubts still, go for equivalent circuit, or if you don't want equivalent circuit, write the truth table. You have A, B, C, okay, 0, 0, 0, 0, 0, 1, 0, 1, 0, all the way up to 1, 1, 1. For each input combination, by visual observation, write down what is the value of the output. You will get the truth table. Once you have the truth table, it is clear. You can be able to guess what is the function. Is it matching with A, B, C, the whole bar? Okay. So that is 3 input NOR, and the last gate we will do is okay. Same logic from here to here. Whatever the structure, the original transistors were connected in, just extend that by one transistor for both the PMOS and the NMOS. There the PMOS were connected in series, so one more PMOS in series. NMOS were in parallel, so one more NMOS in parallel. So you can go easily from two. So both are there actually, 2 input NOR to 3 input NOR. 4 input also same. I'm not going to draw, okay, but there are some for example, in the 4th unit, 4 input gates also will come into the picture, but that is a same extension for NOR and NAND. Okay, so we will not draw those circuits. You can extend it yourself. That is the first thing. And the second thing is, generally there are no basic gates beyond 4 inputs. You can do, of course, anywhere. Suppose nobody says it is not allowed to have A, B, C, D, E, F, G, for example, an expression. But generally, when you have something like that, for example, A and B and C and D and E and F and G, okay, the way in which it will be converted into the netlist, okay, if you remember the VLSI design flow, we have our RTL code, and the tool converts that into a logic level netlist. When it is doing that conversion, it will not convert it into one 6 input AND gate. It will convert it into a combination of a 4 input gate and a 2 input gate. Okay, and as we will see in the 4th unit, the reason why that is done like that is it is actually faster. It is more efficient in terms of speed to have 4 input and 2 input rather than one big 6 input gate. So even in the standard cell library, if you remember during the VLSI design flow, one of the most important components of modern VLSI design is standard cell library. Using that, we can implement any design. Okay, so the standard cell library will have at most a 4 input NAND and a 4 input NOR. You cannot find a 5 input NAND or NOR gate. So that is something that we will prove also to ourselves when we come to the 4th unit. Okay, so this is the basic gates 2 input and 3 input. So one more thing that we wanted to discuss, we discussed this in the slides, but it's important, so we will do another version, not the same thing, okay? Okay, so this is a very important topic to support the way in which all modern CMOS circuits have a particular structure. And why they have that particular structure is supported by the analysis that we are going to do here. Okay, and basically what we are trying to justify in all the gates that we saw, the PMOS transistors were always above, okay, and the NMOS transistors were always below. So the question that we are trying to answer is, why are they in that particular form? So you could have PMOS transistors below and PMOS transistors above, which means that I can work with a simpler technology. I don't need CMOS technology. I can just use PMOS only technology, which is going to be cheaper, right? That is, if I have PMOS transistors above and below. And likewise, completely replace all the PMOS transistors with only NMOS transistors. Have only NMOS transistors above and only NMOS transistors below. So again, I don't need CMOS technology. I can have only NMOS only technology. And both these were prevalent, but there are some issues in the operation. So that is what we are going to see here. And they are not exactly, I would not call them as imperfections, even though the textbook has used that term. It is just a natural consequence of the properties of the transistor. So the transistor is not having any imperfections, but by using them in circuits in any random way, okay, we can create some imperfect circuits. So that is what we are going to see here, which exactly is the cause of that imperfection, so that we can avoid it. So we saw one example in the slides where we have NMOS transistor. We'll see an alternate example here, and then we will summarize, where we have a PMOS transistor, okay. So in all the circuits that you saw, the PMOS transistor was in the top part of the circuit. Now what I'm going to do is, I'm going to put a PMOS transistor in the bottom part, okay, and see what is the problem that we can have because of that. So we will draw the circuit. So I will draw it here. Okay, so this is my situation. I have put the PMOS transistor in the bottom, and since we discussed that I will design circuits such that the output will be connected only to VDD or to ground, but not to both. Here, the top part, I don't even know what is there, but according to my design, it's going to be open circuit, because in the bottom part, I am having input equal to 1 for my gate. Okay, so this is the situation. This is going to create a problem, okay, and we will see what is the problem by analysis of the circuit. Now one thing is, this means that the output is transitioning. The output is changing from logic high to logic low, from VDD to ground, and it has to happen through the PMOS transistor only. So we will divide this into cases just like we did in the NMOS case in the slides, and in each case we will see what is happening and eventually what is going to be the problem. So we will start with A. Okay, so each case, what is changing? Can you tell me? There are some things here, and based on this circuit, I have say A, B, C, D, 4 cases. In each case, what is the thing that is changing in our analysis? What is changing is the value. This is a transition, right? So we're going to be at different levels in the transition. So we will start with output equal to, output equal to 2 volts, which is logic high. Okay, and another thing, this is our situation, and we have to mark the drain and source terminals. Gate terminal, there can be no doubt. Okay, it's connected to the gate, and drain and source terminals we have to mark, and we cannot mark that arbitrarily. Okay, the drain and source terminals are related to the direction of the current plus the device type. So this is a case where there is some positive charge here. Okay, that positive charge is corresponding to logic high or VDD, and that charge has to be removed, and it cannot be removed in this direction because this is an open circuit. So definitely the charge has to be removed in this direction, which means that the charge will flow like this, which means that is the current direction. Okay, and since the current direction is from top to bottom, the direction in which the holes have to move, okay, is the same direction, because this is the direction of positive current. Holes are carriers of positive charge, so they will also move from top to bottom. Now, which is the source and which is the drain? We always said source is where the carriers start from, drain is where they reach. So they start from this terminal and they reach the bottom terminal. So arbitrarily in any circuit we cannot draw. Okay, based on the current direction we have to mark the source and drain plus the device type. So in this case, based on our analysis, we have the 3 terminals of the transistor. So I can also write Vs equal to 2 volt, Vg equal to, sorry, input not equal to 1, input equal to, sorry, input equal to 0, otherwise the PMOS transistor is not going to be conducting. I don't know how to, I can erase it, but I don't know how to go back and change the video. So you have to somehow do it by magic, I guess. So we'll not worry about those. For now, this is the correct case. Vg, okay, is equal to 0. And what is the value of Vgs? Therefore, okay, 0 minus 2 volts, and minus 2 is minus 2 and VTP is minus 0.4. So it is going to be lesser, which means transistor is on, because this is a PMOS transistor. VGS has to be lesser than VT for the transistor to be on. So transistor is on, which means on. Okay, and let's also find out the region of operation, because this is a good exercise with the PMOS transistor. For both NMOS and PMOS, remember that if the drain and source voltage difference is high, okay, generally it means it is in saturation. If the drain and source are at close levels, maybe Greater than, lesser than doesn't matter too much, okay, because in NMOS they need to be greater than, CMOS they need to be lesser than, all that is fine. But if the level, okay, that the magnitude of VDS is low, it means they are in saturation. So by that analysis, if you see this diagram, drain source voltage is quite high because source is at 2 volts, drain is at 0 volts. So VGS, okay, VDS equal to minus 2 volts, and I have to compare this to VGS minus VT, that is minus 2 minus of minus 0.4, which is minus, this is VGS minus VT, minus 2 plus 0.4, and which is greater, don't, minus 2 is not greater, okay. VGS minus VT is greater than VDS. Since this is a PMOS transistor, this is in saturation region of operation, okay. So here, so I'll stop, I'll start because I'm not very sure about this camera. We'll take a break and start the next video after 5 minutes, okay.